Hi everyone, I'm Davi Maximo, and this is my first video lecture on the second Geometric Analysis Festival. We'll be talking about the geometry and topology of three manifolds of positive scalar curvature. So I want to first discuss some basic results in 2 and 3 dimensions that serve as motivation for the principle behind the result I'm going to present later. And this principle is basically the principle that positive curvature implies geometric smallness. So let me show you what I mean by this. So if you take a surface in 2 dimensions with positive curvature, we know by the uniformization theorem that its topology must be that of a true sphere. And moreover, actually, if you, instead of just saying that the curvature is positive, you should actually assume that if you quantify how positive it is, if you assume that it's greater or equal than some constant kappa, then by Bohn-Myers and volume comparison, you actually can show that the diameter of that surface, it's bounded from above by an explicit constant, and so is the area. So in other words, in 2 dimensions, you can state that positive curvature is giving you a topological classification, but also geometric smallness. So this manifold cannot be bigger, than these inequalities are saying. So you ask ourselves, how about 3 dimensions? What of that principle generalizes? And I think the natural curvature condition to look at, it's Ricci curvature at first. So that result you can show using this Hamilton's paper where he introduced Ricci flow, that 3 manifolds of positive Ricci curvature must be diffeomorphic to a spherical space form. And moreover, if you use Bohn-Myers and volume comparison, you get similar geometric smallness. You can get an upper bound on the diameter and an upper bound on the volume of such manifolds if you assume a positive lower bound on Ricci curvature. So the goal of this series of videos will be to show a recent result that I obtained with Evgeny Lyukmovich that extends this to metrics of positive scalar curvature. And I say extend this in a proper sense because we have to be precise. The sort of naive generalizations, they don't work, and I will explain why in the next slides. Okay, so for the purpose of these talks, let's assume now that AMG, it's a closed 3 manifold with positive scalar curvature. And I want to stay in the orientable world. So every time you see a manifold or a surface, you can assume that it's orientable, two-sided. You can extend what I'm going to say to non-orientable, and you also, in that case, you will need to consider one-sided surfaces for sure. But things go through that. You just take my word for it. Okay, but for sake of presentation, let's just say that everything here is orientable. Okay, and we were going to assume that we have a positive lower bound by lambda on our manifold. So what is scalar curvature, by the way? So since this is a mini course style of video, let me just quickly tell you a cute definition. So if you take around the point, if you consider a special kind of coordinate, so in other words, if you take the Taylor expansion of the metric, right, applied to a Jacobi field along radial geodesic in this normal coordinate system, you have that the metric G can be written as the Euclidean metric delta ij, and you have no first order terms, but then in second order, you have this Rijkl term here, which is the Riemann curvature. right? So basically scalar curvature appears when I use this and we calculate the volume of small balls, okay? So if I calculate the volume of a ball radius epsilon around point P with the metric G and also with the metric delta, and I compare the two, I get that the scalar curvature gives me this error. So this is saying that, at least for infinitesimally for balls, this is saying that scalar curvature is telling us that the volume has to be smaller than the Euclidean. So maybe it's an evidence of a geometric smallness, but at least at that small scale. But in fact, this is a very cute definition of scalar curvature, but unfortunately, it has not known to have been ever used to prove any fact about scalar curvature, but it's cute anyway. So I wanted to leave it at there. Okay, so basically, this definition also serves the purpose to give you a kind of a feel of scalar curvature. So basically, we took this Riemann tensor and we traced and traced, by computing the volume, and we got this quantity, and it's a fairly weak quantity, as you can see. So I will show you in the next slide why I say that it's weak. So what do I mean by that? So scalar curvature is weak. Well, it turns out that if you give me any function on the manifold that is negative somewhere, let's say it's at some point it's negative, then I can actually prescribe that function as the scalar curvature of symmetric. So that's a result that it's proven by basically using PDEs. So you can actually get very far into the prescribing the scalar curvature. This is something that you couldn't even dream of with that generality for other curvature conditions like multi-curvature, second curvature. But certainly for positive scalar curvature, you can do that. And as a result, any manifold with boundary, any compact manifold with boundary, you can put a metric with positive scalar curvature on it, because you can just take the manifold and you can double it, right? And on the double, you just select the function that is negative in only one half of the double. So it means that on the other half, which is your original manifold, that scalar curvature is positive, okay? Another fact that it's actually very relevant for our talk is that the connected sum of manifolds with positive scalar curvature also admit a metric with positive scalar curvature. So in other words, if I have a manifold here, A, and another one B, I can select these two disks, and then glue them together. And so if A had a metric with positive scalar curvature and B also had a metric with positive scalar curvature, one can show that this new manifold A connects on B would also have a metric with positive scalar curvature. And that already spells trouble for the question of geometric smallness, because if you think about it, then if I just have one manifold with positive scalar curvature, and I start taking connected sum of itself, right? It seems that as long as my bound doesn't generate to zero, which you can actually show that it doesn't, that manifold is getting very, very, very long. So I cannot prove that the diameter is bounded. So you see that the scalar curvature somehow, the geometric smallness assumption, it's if there is one, it's not as just a straightforward generalization. You cannot bound the diameter from above. Okay. So all right. So I told you that scalar curvature is weak. So now let me actually tell you that scalar curvature is strong. Okay. So in fact, over the years, there has been some topological obstructions found for a manifold to admit a metric of positive scalar curvature. So there is this so-called A hat genus, which is an obstruction that you have on spin manifolds. So it's special to that particular kind of manifold, but it's very, very useful there. And you also have some odd restrictions that were found using minimal hypersurfaces. And these will be important for the rest of our talk. I mean, we'll be talking quite a bit about minimal hypersurfaces later. So in general relativity, scalar curvature also plays a big role because it's the Lagrangian density of the Einstein-Hilbert action. So it plays a role in several important theorems like the positive mass theorem, the Penrose inequality. So it's definitely a strong player in the field of general relativity. And in fact, for our particular interest in this talk, which is 3D manifolds, scalar curvature, it's strong enough that one can classify the topology of manifolds with positive scalar curvature. So you see in the previous slide where I told you that scalar curvature is weak, I say you can prescribe as long as it's negative somewhere, right? You can prescribe that function as scalar curvature of a metric on any manifold. Well, but it turns out that that's key, that is negative somewhere. If you want to push that to positive, you run into problems. So, because then you would have restrictions. And in fact, if you combine the work of Shen and Yao with the work of Perelman, you can conclude that a 3-manifold of positive scalar curvature has to be diffeomorphic to a sphere, 3-sphere, connected some with a list of physical space forms. So in other words, manifolds that are diffeomorphic to S3 mod out by a finite subgroup of SO4 acting freely. So for instance, like land spaces and so on. And you can also have S2 cross S1s. So you can have that. And basically that's all you can have. It's just like this, a list. Okay, so that would be the topological classification. This is our uniformization theorem for metrics of positive scalar curvature. Okay, so let me, before going to the smallness that I want to, discuss later, let me say a little bit of how this theorem is proven. Okay, so basically, what happened here was that in the 1970s, Shen and Yao, they made this fundamental observation. It is really an observation. It's not very complicated to prove, but it's a fundamental observation. It was that if I have a manifold positive scalar curvature, then any closed two-sided surface that minimizes the area, and here I'm willing for it to be a surface that minimizing area up to second order. So what does that mean? It means that maybe it's not an actual minimizer of area, but only when I look at the variations and I look at the second derivative of how the area is varying, I get the correct sign for that variation. Then this still applies. So we call this kind of surface stable. So if a surface minimizes area up to second order, stable minimal surfaces. So what they showed is that a stable minimal surface on a 3-manifold positive scalar curvature must be a topological true sphere. Okay. And basically then using that fact in an area minimization scheme for incompressible surfaces, they classified the fundamental group of 3 manifolds of positive scalar curvature. Okay. Now, back then, it was not the topology of a 3-manifold was still not understood from its fundamental group. There was this, famous problem open, the point correct conjecture, which was the somehow the fundamental case is when you are simply connected, must you be a sphere? So once that was worked out by Perelman in his solution of the point correct conjecture and geometrization, then if you combine those two things, you get that you can classify the fundamental group and also the topology of a 3-manifold of positive scalar curvature, and you get the list that I showed you in the previous slide. Okay. So So let me just tell you a little bit how this minimization scheme for a compressible surface works and why you find the fundamental group information out of it. So I'll do that in the case of the three towers. So suppose we have the three towers and we have a metric on it, right? And basically what we do is we're gonna take a two towers inside that three towers, and we're gonna look at how the fundamental group, so we get an action from the fundamental group of the two towers inside the fundamental group of the three towers. And you can see that we can select one that is injective. So this is what it means to be incompressible. So in other words, pick a two torus here that the fundamental group of these two torus, the inclusion of these two torus in the three torus inject that fundamental group. Okay? So it turns out that if I consider now two torus such as this, I can, start moving these two torus a little bit. And at first, I mean, it will maintain that that property of injecting the fundamental group. So I start moving around, and what I do is I minimize the area. So I start moving around, trying to make that smaller, and it turns out that they proved you can find a representative, right, that has the same action the fundamental group level, but it has the smallest area among all such representatives. So this is this red minimal surface here. And this guy will be a stable minimal surface. But if it's a stable minimal surface, and because the fundamental group injector has to be the same, well, it means there is a two torus, right? I mean, it's going to be basically a two torus. So you then can say, well, but a stable minimal surface in positive scalar curvature has to be a topological sphere. So, and here's a two, and here's a two torus. So contradiction. So in other words, the three torus cannot admit a metric of positive scalar curvature. Okay, and basically what you do is you now consider more general manifolds, and what you do is you look at surface groups inside the fundamental group of that manifold, and then you try to play the same game. Maybe you find a two torus or three torus or four torus. So the conclusion is that you can only have spheres. So if we go back, the connected sum, right? Basically, you see all these pieces, they don't have, you can only have stable spheres here because, it has three, and then you can maybe have a stable two sphere here where the connected sum is happening, but that's fine, right? And also you can have a stable sphere on these factors S2 plus S1, that's okay. But you cannot have a stable minimal surface of higher genus. Okay, so yeah, so this is basically the result that gives you the topological classification. Okay, so how about geometric smallness for these guys? Okay, so for geometric smallness, the whole point is that we have to go back and look at the fact that you can do connected sums with positive scalar curvature. So those manifolds, then they don't have to be small necessarily, because you can start with one piece, and then you can start doing connected sum with itself, and you can keep going in a direction as long as you want, right? You can keep going. So this is just you can keep elongating, and you can get like a somehow long kind of looking manifold like this picture here represents. Okay, in case you were wondering, this picture here, this is not a surface of genus 8. It's just that you can't do connected sum, and somehow if you play your game right, you can actually start doing connected sums like this, and then later maybe you can try to join them. It's potentially complicated, okay? But the observation is that this somehow this longiness, that right, this sort of big size that you can get by doing connected sums, this can be captured maybe by codimension 2 data, right? So in other words, if you look at this manifold here, this long manifold of positive scalar curvature, it is long, but really it's long, like there is this one direction, which is like I'm doing disconnected sums, and along them I'm growing. But if you look at the connected sum construction, you have like a cylinder, and that cylinder cannot be very, it can be long, but it cannot be very fat, right? So maybe modulo a codimension 2 data, these guys have to be small. And in fact, there is a conjecture by Gromov that states that if you for every manifold of positive scalar curvature, there exists a polyhedral complex for dimension 2 and a map from M2, that polyhedral complex, such that for the pre-image of every point in the polyhedral complex by this map, so the fibers, right, they will have bounded diameter and bounded area, where C is a universal constant here that doesn't depend on the manifold, only on the lower bound on scalar curvature. Okay. So this, I believe, is the right frame of posing a question about smallness of positive scalar curvature. So somehow there is nothing we can do about it getting long along a certain direction. So if we unwrap this to 3 dimensions, then basically we're saying that modulo this one graph, the manifold, it's small. So let me show you what we proved. So we showed that if you take a 3 manifold with positive scalar curvature bounded below by lambda, then there exists a metric graph gamma and a continuous map such that for every point in the graph, the pre-image of that point has area controlled, also the diameter. And because these are going to be surfaces, most cases, these are going to be surfaces, we also bound the genus. So in other words, this is saying that manifolds, 3 manifolds with this lower bound on scalar curvature, they have to be geometrically small modulo this graph. If you go very, very far away from them, you know, take your glasses off, what you see is this graph really. If the, you know, so the manifold is small. And you can actually rewrite this theorem maybe in a more conventional way by basically changing this map a little bit. You can say that there is actually going to be a Morse function such that the connected component, each connected component of the pre-images, right, have controlled area, diameter, and also genus. The constants get a little worse, but you can modify Theorem A and prove this Theorem B. Okay, so the goal of for the remainder of these videos will be to prove Theorem A. So we're going to focus on that. And I'll try to give you an idea of how the proof goes and what are the sort of ingredients that we used, and also some of the difficulties that we had to overcome. Okay, so let me just go to this slide, which is basically if I apply the theorem to that manifold that I had drawn earlier. So this is what we should have. Okay, so along gamma, it can be long. Along this one-dimensional graph, it can be kind of long, but across it, it cannot. That's one way of stating small. Okay. So what is then the methods and the way that we go about proving this? Okay, so the basic observation that we had is that when you have a manifold with positive scalar curvature and a lower bound like that, the lower bound on scalar curvature does give you geometric smallness for certain kinds of minimal surfaces. Okay, so namely, when I have a manifold of positive scalar curvature, and I have a minimal surface inside there that has either index 0, so in other words, stable, or it has index 1, which basically means that it might be unstable. So in other words, there is one direction where I can decrease the area, but essentially that's the only direction. So that's why we say index 1. So essentially one direction where you can decrease area. Then you do have, from the lower bound on scalar curvature, you do have geometric smallness of those surfaces, okay? So from that observation, we say, okay, so how can we somehow extend that to the rest of the manifold? So basically our strategy for proving Theorem A will be first to observe that positive scalar curvature lower bound gives the smallness for minimal surface of index 0, 1. So then we want to construct several of them, as many as we can, cutting up the manifold along them into several connected components. And then we can foliate, right? We want to foliate these connected components in a way that we propagate those area and diameter bounds. And so basically what we do is we'll start foliating the region. So it's going to be, we cut along minimal surfaces, so we're going to have a manifold boundary, and the boundary components are small. Now we want to just, start foliating that. And as you see, this foliation is what will give you the graph. Now we say a singular foliation because it can split. We can start with a foliation. We can start foliating some surfaces, but then it could come a point where it can split, right? Foliate this direction and that direction. In the context of finding the graph, that's actually fine. It just means that the graph split open. Okay. So that's what we'll do. So I'll finish this video for now, and on the next video, I'll start talking about the proof. So we're first going to talk about this decomposition, right? Cutting up these surfaces, and then we'll just discuss propagating area bounds first. So for that, we're going to use main curvature flow, and then later we're going to see maybe on the third video a method that we use to how get those to modify that foliation by mean curvature flow into one that gives us also diameter bounds. Okay, so I'll stop the video now and continue the next one.